Okay, thanks. I'm Ed Large, and I'm here from my new university in Connecticut. Last time I was here, I was from Florida, actually. And I just want to start by acknowledging my graduate students, my collaborators, and the funding institutions. A lot of this work here, you'll see, was done by Mark Velasco, and some of the experimental results in collaboration with Ilana Galambish, David Poppel, and Charlie Schroeder. So this perspective that I want to share with you on rhythm is a perspective on the neurodynamics of rhythm perception. And it begins with this sort of observation that Jaime pointed to yesterday about this continuum between pitch and rhythm. So, you know, if we start out and we think in terms of time scale, the time scales, the neural time scales that are associated with pitch begin at about 30 hertz and extend out to, you know, several thousand hertz. Whereas the neural time scales that are associated with rhythm, you know, begin at about 8 hertz and continue into the lower frequency directions. And, you know, we could take an impulse and we could repeat that impulse every 5 milliseconds. Let me just check my loudness here. And we could listen to that. It would be a 200 hertz repetition rate for impulses. A little loud, but you get the idea. Then we get the percept of pitch. But now if we change that inter-impulse interval from 5 milliseconds to 500 milliseconds, of course we get a rhythm, okay? Now, that leads me to hypothesize that it may be that there are very similar mechanisms in terms of the neurodynamics responsible for the percepts, just operating at different time scales. Today, I'm going to be interested in the time scale of rhythm. And so what I want to do is I want to compare that 2 hertz rhythm to cortical rhythmicity in humans. So, for example, let's just see here. Okay, that 2 hertz rhythm, which is a preferred rhythm for humans, a preferred frequency for humans, lies sort of right in the middle of the delta band, the cortical delta band. That doesn't quite extend all the way up to the top frequency for rhythm perception in humans. To go from about 4 to 8 hertz, we're looking at the theta band. If you extend then into that sort of no man's land where sounds are neither pitch nor rhythm, you're looking at the alpha band and the beta band. Beta band is the frequency band at which a lot is happening, of course, in the motor system. And then 30 hertz and above for cortical rhythms, we usually refer to that as the gamma band. We could also ask what sounds sound like if we play them, for example, in between 2 hertz and 200 hertz at 20 hertz. That would be the beta band. And we're going to hear a kind of a roughness percept, okay? So today what I want to talk about is an approach to signal processing that I think of as a neural kind of signal processing that's based on dynamical systems theory, okay? I want to begin by discussing what we know sort of empirically about acoustic rhythms and the relationship to cortical rhythms. So 15 years ago or so, Maury Jones and I proposed what's known as dynamic attending theory these days, in which we proposed that essentially what happens when you listen to a rhythm, especially a musical rhythm, is that it would entrain self-sustained oscillation and direct pulses of attentional energy to expected points in time. Okay, we modeled that using a very simple model of neural oscillation, and we showed, and a number of people showed since then, with behavioral and perceptual experiments, that in fact this does explain perceptual data. In the early 2000s, Joel Snyder came down to my lab in Florida, and we made the following sort of hypothesis that, you know, if this is really what's going on when humans listen to rhythms, then this should be something that should be directly observable in human EEG. Oh, thank you. Okay. So here we have 1, 2, 3, 4 different experimental patterns we used: a periodic control pattern, a loud, soft, and then of these loud, soft patterns in which in C here we're omitting the loud event sometimes at random locations, and D we're randomly sometimes omitting the soft event. And then this thing labeled metrical percept would be the predictions of dynamic attending theory. Okay, and importantly for this experiment, that if you left out, for example, the loud event, you would still get a peak here, some kind of rhythmic expectation. Okay. I'm not going to explain the results of that entire experiment because I've got a lot of things I want to get to here. But when we looked for neural correlates of pulse in beta and gamma band rhythms, so these are the higher frequency rhythms, what we found is, and here we have the onset of events here and here, so this is 2 rhythmic cycles, and this is 20, 30, 40, 50, 60 hertz going up here. We found, as a response to the event, we found a little cluster of a little hot spot at about 25 hertz that followed the onset of events with about a 50 millisecond latency. And here we have a sort of a stronger response and a weaker response that could be some sort of spontaneous rhythmization, so-called. Okay. Now, but when we looked at the amplitude fluctuation in the beta band rhythms, what we found was that we had 2 hot spots of amplitude fluctuation that peaked just before the acoustic event occurred. So here's a peak here, and here's a peak here. And what we hypothesized then is if we looked at this so-called evoked response, this represented a response to the sound, whereas this induced beta band represented an anticipation of when the sound was going to occur. Okay. Now, a couple years after we published that paper, I was visiting up in Montreal, and I showed, let me go back here for a second. So I showed Robert Zatori those results. And you notice this evoked response happens sort of in FCZ, which is approximately where you expect to see auditory. But this induced response was more frontal and lateralized in every subject, although sometimes it was on the left, sometimes on the right. And I said, Robert, what do you think that represents? Where is that coming from? And he said to me, oh, that's motor activity. And I didn't believe him. I said, no, that's crazy. It's attention, right? That was our hypothesis anyway. But a year after that conversation, his group, and with Pen Hyun and Joyce Chen, showed that, in fact, if you simply listen to a rhythm without moving, listening to that rhythm activates motor cortices as well as auditory cortices. So here you're looking at supplementary motor area, premotor cortex, and so forth. Okay, cerebellum. So these different motor regions, which a lot of people, including myself, were pretty surprised about that at the time. And Jessica Gran, a year later, Gran and Rowe, showed, in fact, activation of basal ganglia and greater subcortical cortical connectivity when the beat was more salient in a rhythm. So now we've got a motor network being activated when you simply listen to a musical rhythm. Okay. Now we're getting to more recent history. In 2011, what I felt was, really a breakthrough result was reported by Sylvie Nazarden and her colleagues, including Isabelle Peretz. What they did was they played a rhythm that had a pulse at 2.4 hertz, and they recorded delta band activity. Now remember, delta band is the frequency band at which pulse typically occurs in music, or it's perceived to occur in music. So when they played that rhythm, which was constructed in a particular way that I'm not showing you, they get, and they record EEG, and then they take the Fourier analysis of that EEG. They show a nice peak at 2.4 hertz. Now they instruct people to subjectively impose a 2-beat grouping. Okay, so you're subjectively imposing strong, weak, and look what happens. They get a very, very nice subharmonic, second subharmonic, right here. So the blue is the average, and then these gray behind are the individual subjects. So it's happening in pretty much every subject. And then when subjects are instructed to imagine groups of 3, a third subharmonic, and then a harmonic of that. So something really, really interesting is happening when people listen to rhythms. And this is auditory activity, by the way. So what seems to happen is delta band entrainment, and then an amplitude fluctuation in the beta band, which is essentially doing what that delta band entrainment is doing, and That's consistent with this perspective of Lakatos and Schroeder, reported first in 2005, of an oscillatory hierarchy in auditory cortex in which the phase of delta band oscillations controls the amplitude. Well, here they're showing the amplitude of theta, but in the musical context, we're seeing that the amplitude, that the phase of delta is controlling the amplitude of the beta oscillations. Finally, one last result. This is something that I did in collaboration with Takako Fujioka and Laurel Traynor and Bernhard Ross up in Toronto. We were interested, I originally approached them to try and replicate this result with Joel Schneider using MEG, magnetoencephalography. This group ended up doing a little bit of a extension of that. So Joel Schneider and I used 390 milliseconds. We added then 2 more tempi and then a random rhythm. And what we showed is that what happens is if 0 is the onset of the event, what you get is a peak right about at the onset of the event, and then a desynchronization of beta, and then a resynchronization that temporally anticipates where this next thing is going to occur. And we measured this half max point, and we showed that the half max point is really, it changes systematically depending on the tempo that you're listening to, so showing that that's an anticipation. Now, because it was MEG, we were then able to localize where this activation is coming from. So this is an auditory response, and then we looked for other parts of the brain where the response is correlated to this. Remember, these are amplitude fluctuations in beta, and what we showed is a network of areas that's quite similar to what Zatori et al. Showed. So these are parts of the brain in which amplitude fluctuations in the beta band are anticipating the rhythm, okay? And it's not a coincidence that these are amplitude fluctuations in the beta band, because now the beta band is the frequency band at which the motor system operates. So there seems to be a communication happening between the auditory and motor system using fluctuations in beta band power. Okay. So just in summary, we started out with dynamic attending 15 years ago, and when we look for neural correlates of dynamic attending, what we see is entrainment in the delta band with controlling amplitude fluctuations in the beta and the gamma band. We see that there's motor system involvement that's consistent with Schroeder and Lakatos's oscillatory hierarchy, and an interaction between the auditory and motor systems that appears to occur in the beta band. Okay, so what we want to do now is we want to create a kind of a model, a neural model that's going to help us to explain these observations. Okay, now when we're looking at auditory or any cortical oscillations, these usually arise through an interaction of excitatory and inhibitory populations of neurons connected in this reciprocal way. And that kind of network generally can produce a lot of different kinds of behavior, including this tonic spiking or this rhythmic bursting behavior, which may be what we're looking at in this kind of a system. So what we do is we write down some differential equations here in which X describes the excitatory subpopulation of neurons and Y the inhibitory subpopulation. These are just very general equations. And then we write it with tau here such that tau is a time constant such that the frequency is equal to 1 over tau. Okay? And then we array these according to a frequency gradient. So low frequencies at one end, high frequencies at another end, and we connect them together in a particular way. Okay? And then, of course, we stimulate them with sound. Okay, so you might think of this as sort of auditory and motor, and in fact, we will characterize it in that way in a minute. I just want to show you where our predictions come from. So our predictions come from an analysis of those equations in which we take the more realistic neural level model, which might predict this sort of ovoid shape in the state space. So this is the time amplitude plot, and then this is the state space. And we do a coordinate transformation that takes that funny shaped limit cycle and produces a perfect circle. And what that does for us is it enables us to write down equations in terms of trigonometric functions that we can solve. And we can make closed form predictions about what this model is going to do. Now, when a mathematician does that kind of analysis, they end up with an equation that looks like this. It's called a normal form. And this normal form, this is a complex number. It has both a real and imaginary part. Think again of the excitatory and inhibitory subpopulations. And you get an equation like this, which describes a Hopf bifurcation. This is the input, and you get these higher order terms. Okay, now usually a mathematician will ignore those higher order terms and say, this is mostly what I'm interested in. But we decided, since we wanted to characterize signal processing in a system like this, we should expand those out and see what they look like. So we wanted the complete expansion, and this is really a Taylor expansion of the nonlinearities. So we come with a canonical model like this, where these higher order terms are here and here. Okay? I won't say too much more about that. But I just want to show you what these higher order terms do for you. So there are at least 4 different kinds of qualitatively different dynamics that can come from a system like this. The first, if you just leave out the nonlinear terms, is linear. So this is the strength of the stimulus, the amplitude of the stimulus versus the amplitude of the oscillator response. So this can be a linear filter, okay, a bandpass filter. If you now take just the normal form, you can describe a critical nonlinear oscillator, which has a fixed stable point at 0, no oscillations, but this very fast growth of this amplification and then compression. You can describe a limit cycle oscillator, so a stable limit cycle whose amplitude grows a little bit when the stimulus increases in amplitude. And you can even get this kind of fancy, cool stuff. This is called a double limit cycle bifurcation. So you have 2 fixed points. This is a quiescent fixed point, so there are no oscillations in the absence of stimulus. But you give a little stimulus, and the system jumps up to a limit cycle, and then if you take the stimulus away, the limit cycle remains. So this could be kind of a memory. Okay. The other thing that happens in a system like this is you get mode locking. So you can have synchronization of 1-to-1, so 1 cycle of the input corresponds to 1 cycle of the oscillator. But you could also get 2-to-1, okay, so 2 cycles of the oscillator for every 1 cycle of the stimulus. That would be a harmonic. Or you could get this subharmonic, which is the kind of thing that we saw in Sylvie Nazoraddan's data, this subharmonic resonance. Okay. All right, so in summary then, we've got a model of neural oscillation that's based on fundamental neurodynamics, which we think is appropriate for describing auditory music perception, that's 1 step removed from the physiology, but it's analytically tractable. And we're looking here at nonlinear signal processing, spatiotemporal pattern formation, and Hebbian plasticity in systems like this. We're about to release what we call the GrFNN toolbox for gradient frequency neural network toolbox. It will be available at the end of the month. Some of you have already signed up for the release. It's going to be released under the GPU public license and hosted on GitHub. We've got a book on the way entitled Signal Processing, Plasticity, and Pattern Formation in Networks of Neural Oscillators, where we give away all our mathematical secrets. And we're building auditory models of the cochlea, brainstem, tonality, and most relevant rhythm. I have a minute or 2 left. Okay, so let me describe the rhythm model. So the question here, which I think is really interesting, is not what happens when you listen to an isochronous rhythm, but what happens when you listen to a complex rhythm. So here is a moderately complex rhythm. Okay, and the metrical structure, and what we see is we get, when we do a Fourier analysis of that rhythm, a nice peak right here at the perceived pulse. Okay, let's make it a little bit more complicated. Let's make it a son clave rhythm. Sounds like this. And look what happens to the energy at the pulse. It drops down, and there's energy at these frequencies is actually greater. So how do I get that pulse? Okay. If we look at something a little more complicated, a rumba clave, look at that. Almost no energy at that pulse frequency. How does that happen? Well, if we take seriously that empirical data, then what happens is we have some sort of a sensory network or an auditory network and a motor network, and perhaps that pulse is arising through an interaction of these two networks. Okay, so sensory network, motor network, stimulated with a rhythmic pattern. In here we have a limit cycle, describes the sensory network, and this double limit cycle, or this memory exhibiting network for the motor network. And if we play an isochronous rhythm here, this is the amplitude of oscillators in the network, and this is the oscillation itself. Probably not surprisingly, we get a pulse at the frequency, repetition frequency, but also here's a subharmonic arising, as in the Zoradans data. Here's the rumba clave. You want to look at 2 hertz here. At first, it doesn't look too hopeful, but watch what happens. Okay. This pulse emerges from that network interaction. And then we've invented some other rhythms that we call missing pulse rhythms that actually have 0 energy at the pulse frequency. And this will also restore even when there's no energy there, which to me is really the sort of mystery of rhythm perception here. Okay. And I know I'm over time, but let me just show you just a couple more things. So how does that last network work? Well, for an isochronous rhythm, you see the sensory cortex is producing, well, the sensory and motor networks are essentially doing the same thing. But for the complicated rhythm, what you see is the sensory network is producing a pulse for every event. It's effectively a kind of a representation of the input rhythm, but the motor network is now producing a spike on every pulse, okay? And here is the frequency analysis of that, so we're predicting something like this here. A spike at 2 hertz, even though compared to this white frequency analysis, there's no energy there. So the key is then, can we do an experiment that shows that people actually perceive a pulse in that rhythm, even though there's no energy there? And we tested 4 of those rhythms and some simpler rhythms. And the short way to tell this story is for these complexity level 4 rhythms with no energy at the pulse frequency, people are tapping predominantly at the pulse frequency. Okay, so, which is not actually surprising in a room full of musicians. Of course, we all know that's where the pulse is, but we did manage to show it empirically. People are actually worse, though, at tapping the pulse at these complex rhythms. So sometimes they're at antiphase, and sometimes they're just not able to get the pulse. And this is some other more detailed data that I won't have time for. Interestingly, this is the last thing that I'm going to show. In collaboration with Ilana Golombish, David Poppel, Charlie Schroeder, we did some MEG recordings. So this is magnetoencephalography, and we showed that people who are bad at tapping the pulse of this rhythm, who can't get the pulse, you get no energy at 2 hertz. But the people who can tap the pulse, whoops, look at that. Look at that energy coming in at 2 hertz. Okay? So this is a theoretical model that makes real predictions about what's going to happen both at a behavioral level and a neural level when you listen to rhythm. And so far, we've been testing those predictions, and so far they look like they're working out. So thank you, I'm way over time.
So thank you so much. We have time perhaps for one quick question.
Okay. How much of that patterns which you see in the motor systems then would be learned, and how much might be innate?
That's an excellent question. So, so the dynamics are, I wouldn't say innate, but intrinsic to a nonlinear oscillator. But in that network, we wired these together in a way that we assumed would be learned. And I actually anticipated your question, and I've got a little a MATLAB script up here, which makes us a stimulus Here in this demo, okay, what you're going to see is a network that has no input, okay? And you're going to see that even with no input, it's going to wire itself together. So take a look at what happens when I run this MATLAB script, okay? This is the amplitude of connections. This is 1 to 1, that's 2 to 1, that's 1 to 2, that's 3 to 1, that's 1 to 3. This thing is wiring itself up with Hebbian learning without even any input. Now, if I had input, let's say a 2 to 1 rhythm, I get a big hotspot here, okay? But if you set the parameters right, this thing will wire itself. So we made some assumptions in that network about how it was wired. We didn't bother with the learning, but we're now also exploring Hebbian learning. So we hope maybe we could do some of the more unusual rhythms like you were showing that you've had success with.
Maybe one final, very quick question.
Hi. How might you predict this model acting on if people were asked to do a motor task that was supposed to confuse or, I mean, have you tried to perturb the system?
No, that's a really good idea. That's not actually something I've even thought of. That's a really good idea. That's something we should try, absolutely.
I'd be happy to know what happens.
Okay.
Okay. Thank you very much.